Swayam Prabha. Digital India. Educated India.
All right, so let's just recall that where we paused was our understanding of what is possible when it comes to designing mechanisms with certain properties. And the last thing that we saw was that it is not possible to come up with a mechanism which is simultaneously onto strategy proof and non-dictatorial. That is where we stopped, right? We didn't actually prove this, but we just built our way into understanding that strategy proofness implies monotonicity, strategy proofness and onto implies unanimity, and based on monotonicity and unanimity we sort of got some intuition based on examples for why what we are saying might be true. But as I said, I'm deferring an actual proof to later. By later I mean hopefully during one of the tutorial sessions we'll have a chance to revisit it. But I want to continue the story by talking about what can we do to work around these impossibility results that make it seem like coming up with good voting rules is not something that we can hope for. So informally these rules are saying that you can't make everyone happy all the time, which is intuitive but at the same time not something that we want to live with. And I also mentioned that if you think about the last impossibility result that we saw, two things that we could try and do are A, randomization, and B, trying to see if we can quantify the extent to which we are giving up on strategy proofness. And we also briefly mentioned that both of these approaches, there's a formal sense in which both of these approaches in fact also fail. So now I'm finally going to present some positive news. I'm going to talk about approaches that do work, and the first one is this really nice notion of restricted domains. The idea is that we would like to see if there is a sensible subset of profiles that we can carve out and focus our attention on, in the hope that maybe these are some well-behaved profiles on which we can hope to design mechanisms that do better. And it turns out that this has become a fairly fruitful way of looking at things and has led to some interesting lines of research. And I'll focus on one such set of approaches, and there are several others. I mean, there are many ways in which you can carve out pieces of this big pie, which is the set of all profiles. I'm going to focus on a specific way of doing it, which is called the notion of single peaked profiles. If we have time, we'll also take a peek at what it means to talk about single crossing preferences. So I'm going to start by trying to present the definition of what it means for a profile to be single peaked. Okay, so let's motivate this by considering maybe a typical political situation where you have candidates whom we line up based on their philosophies. So that's why we have left, center and right. And so A and G are the extreme candidates. A is extreme left and G is extreme right. Okay. And you can imagine that a particular voter's preferences over these candidates would typically not be completely arbitrary. When we were looking at the space of all possible profiles, we were really considering all kinds of weird combinations of votes. But let's say that this is a specific situation that we are in. Can you imagine a voter that ranks A as her top candidate and G as her second favorite candidate? Is that realistic? I mean, it's a soft question. I mean, of course, formally a permutation is any ordering of the candidates and this would be admissible. But if you just think about it, a voter that places A on the top is presumably a left-leaning voter. If she likes an extreme left candidate as her favorite candidate, then it is very unlikely that she will pick an extreme right candidate for her second spot, right? It's probably going to be a softer transition where maybe it goes like A, B, C, D in that sort of a sequence, right? Imagine a voter whose favorite candidate is D, which is a candidate who is in the center, and then again to think that D would be immediately followed by A or G seems unreasonable, right? Because if your favorite candidate is somebody who is in the center, then you are probably not somebody who is extreme, and you would probably not immediately have a preference for the extremist candidates just after you have indicated that the candidate in the center is your top preference, right? So some combinations seem to be unreasonable, like I said, A followed by G or D followed by A. These combinations seem a little unrealistic. So let's try to propose a definition that accounts for this intuition and says that, well, we are just going to rule out permutations which don't seem to follow the natural instinct that we are being presented with here. Okay, so okay, I need to get used to this, but all right. So here, I don't know if it's visible, but yeah, I'm focusing on the candidate E. Here is a voter who likes E the best. And here is what I'm suggesting would be a reasonable ordering of the remaining candidates. So for instance, let's just focus on the candidates who are to the left of E, right? So that's A, B, C and D. And notice that the way they are ranked here, their relative ordering is D, C, B, A, which is to say that the further a candidate is from A on the left to right spectrum, the lesser the voter seems to like it. And that seems reasonable considering that E is the voter's favorite candidate, right? And if that's where your heart really is, the further a candidate is away from this guy, the less you are likely to be in favor of such a candidate. And the same goes for candidates in the other direction. Okay, so it seems reasonable to say that any voter that likes E the best will prefer D less than E, C less than D, B less than C and A less than B, and similarly will prefer F less than E and G less than F. However, that still leaves you a fair amount of room to construct multiple preferences that respect the criteria that I just suggested. So for example, here is one where I have merged the two sort of, so I guess what I said was that E is preferred over D, is preferred over C, is preferred over B, preferred over A, and we also think it's reasonable that E is preferred over F, is preferred over G. But these two orderings can still be merged in multiple ways. You can imagine interleaving this portion of the order with this portion of the order in multiple ways, and we perhaps have no reason for ruling out any of these interleavings. Any of these interleavings would still be reasonable. So all of those interleavings are in some sense permissible in the framework that we are going to be proposing here. So I probably have a couple of more examples of orders that respect this idea. So here is a different interleaving, and you could do a few others, and you can also easily come up with examples that violate the criteria that I'm suggesting here. So this is a typical pictorial representation of what it means for a preference or a permutation to be single peaked with respect to a universal ordering over the candidates. So this ordering over the candidates, which is A through G going from left to right, this is something that is fixed a priori. Some people call it the harmonious ordering, some people call it the universal ordering. So this is some fixed permutation of the candidates, And we say that another permutation, which is presumably the preference of a voter, is single peaked with respect to the harmonious order if it has the property that if you look at the position of the top candidate in the permutation and then look at the positions of the remaining candidates, then the way they are ordered in the permutation respects the harmonious ordering in the way that we just discussed. Okay, so we'll make this a little more formal, but hopefully the idea is beginning to emerge, or is becoming clear. So here is a slightly more precise definition. We say that you have a preference that is single peaked if when you say that X is liked better than Y, okay, then either X is your favorite candidate, and if X is your favorite candidate, you are allowed to like X more than any of the other candidates. But if this is not the case, then if X and Y lie on the same side of the peak, so I'm using the word peak to refer to the favorite candidate of the voter. So if X and Y both lie on the same side of the peak, then Y must appear later than X in the harmonious order. Y must be further away from X, further away from the peak than X is. Okay. Of course, if X and Y are on opposite sides of the peak, then we are not really bothered, because that's the interleaving that we were referring to. If these two candidates are on either side of the peak, then X can be ranked above Y. There is no problem, right? So whenever we rank, so what is the test for a permutation being single peaked with respect to a harmonious order? So again, let's say that A to G is the fixed harmonious ordering, and let's say that you give me a permutation. My test is going to be that for every pair of candidates, I'm going to check if, so let's say you have ranked B above D, and let's say E is your favorite candidate, right? Then does that pass the test for single peakedness, or does that fail the test for single peakedness? B over D. You say you like B more than D. Okay, how many of you think that B over D would not be a valid single peaked order, assuming that E is the peak? Okay, so yeah, so it turns out that D is closer to the peak than B is, right? So you would want to rank D higher than B, but it could be that the gap between B and D could be, I mean, you can't really control that. You might be ranking F and G in between, or the gap will be at least 2, because you still have to rank C before you can bring in B into the picture, but it could be more than that. But nonetheless, D has to be ranked higher than B if you have an ordering that is single peaked with respect to this order, with E being the top candidate. Yeah. So essentially for any pair of candidates which are on either side of the peak, there is nothing to check. But if your two candidates who are on the same side of the peak, then your relative order must be something that respects the harmonious order, which is to say that if you rank A higher than B, then A must be closer to the peak than B is. Is that clear? That's the definition of what it means for a given permutation to be single peaked with respect to a fixed harmonious ordering, or a fixed universal permutation. Okay. So the situation we are going to consider is, what if your profile only consists of preferences which are single peaked, meaning there exists a universal ordering on the set of candidates with respect to which every vote is a single peaked order. Okay, so remember, they can all peak at different places, so the voters can have different favorite candidates, but once you fix your favorite candidate, you must have this sort of diminishing on either side of the harmonious order, with still some flexibility in how you interleave. That's the kind of profile that we will concern ourselves with. So you could ask yourselves how many single peaked orderings are there with respect to a fixed harmonious order, and you should convince yourself that you can come up with very many of them. I'm not going to suggest how many, but just think about what the possibilities are. Essentially, if you peak somewhere in the middle, then you have these two fixed orderings, but you have various ways in which you can interleave them. So think about how you would enumerate those choices. So that's an interesting question to think about. How many single peaked orderings are there? I mean, it would be a little silly if our definition was so restrictive that there are only a very small number of orderings which respect the definition. Then you wouldn't really be looking at an interesting class of profiles. So convince yourself that there are many single peaked orderings. As I said, I'm not going to put a number on it, just think about it. The other reason why this is a reasonable set of preferences to look at is that there is a lot of literature justifying that these preferences are a reasonably realistic model of let's say real world election instances. For example, I mean, the motivation is right here, and there is some data to support this claim. In fact, I think the definition was also inspired by studies in political science which observed this sort of behavior. So let's just settle with the idea that this is a reasonable notion to propose. There are also other reasons why it's exciting to look at single peak preferences. So as I said, I've already mentioned the last point here. But okay, one thing to worry about is, given a profile, a fundamental question is to check if it is single peak, because without knowing if your profile has this property or not, it would be a little hard to make progress on anything else. Let's say you have a mechanism which works well for single peaked profiles. Before you apply the mechanism, you want to be sure that your profile is in fact single peaked. So it's a nice puzzle to think about. How will you check if a collection of permutations is single peaked or not, right? Does that question make sense? I give you a bunch of rankings and I want to know, can you come up with this universal ordering of the candidates with respect to which each one of these rankings is single peaked? Yeah, so I'm kind of turning the tables now. Previously, for the definition, we were saying that if there is a ranking which is universal, with respect to which every other given ranking has this nice property, then we say that the collection of rankings that we have is single peaked. And now I'm saying, okay, so typically you are given a profile to contend with, to work with. How do you check if it is single peaked? How do you check if there exists a universal ranking with respect to which all of these rankings have these nice properties? So that is one thing to worry about, but it turns out that this is something that you can actually efficiently check. And again, it's not something that we will be getting into, at least not right away. The thing that I really want to focus on is that there is a mechanism with respect to which no agent or no voter has an incentive to change their preferences. Okay, so that makes this a legitimate follow-up to the discussion we had earlier in the morning. So essentially, I'm saying that if your preferences are single peaked, then there is a mechanism which is strategy proof on such profiles. Okay. All right. I'm also claiming that there are no Condorcet cycles, which are these majority cycles that we saw previously, right? So you remember we said that if you look at the majority outcome, so for instance, we said that you could have situations where you prefer A over B. Okay, so I don't remember how I told you the arrows yesterday, but yeah, maybe this is what I did say, that A is preferred over B, B is preferred over C, and C is preferred over A. So that would be a majority cycle situation. So if you're going to get bored for the rest of this lecture, maybe this is something you can wrestle with and convince yourself that there are no Condorcet cycles emerging from single peaked preferences. And remind me if we have a bit of time at the end, we will revisit this. But for now, I want to get to the issue of whether we can come up with a strategy proof mechanism, because that's the thing that arguably interests us the most at this point. Okay, so I'm going to start by describing or proposing a mechanism, and then we will think about whether it's strategy proof or not. Yeah. So what is this picture? So we have here all the candidates, and I have enlisted below each candidate the voters who rank this candidate at their top positions. Okay. So A has 3 voters for whom the peak was at A, right? There are 3 voters who peak at D, for instance, and so on and so forth. So this is the entire collection of voters partitioned according to which candidate they place at the top spot. Okay. All right. Okay. Yes. The mechanism outputs the so-called median candidate, which in this example, I think we find it at D. So what is the median candidate? You basically walk down the harmonious order, okay, and keeping track of the cumulative count of votes that you have received thus far, okay. So essentially think of this as so essentially it's the candidate where the total number of votes that you have collected up to that point crosses half the entire population. That's the median candidate. So do I draw a normal curve based on, okay, you're thinking of this as so if you interpreted this as a histogram, there is no reason to believe that the histogram would have like a normalish shape, if that's what you're asking. Because even in this example, if you were to draw a histogram on the candidates, so you see that there are 3 here, there's just 1 here. Oh, on the single, so I'm actually in fact hiding the rest of the vote. I'm just, so each of these voters have a single peaked preference. So, but for instance, this voter here peaks at D. All of these voters peak at D, but they could have fairly different preferences, right? In the sense that this could be D followed by C followed by B followed by A and then E, F, G, whereas this could be potentially, let's say, D, C, E, B, F, A, G. These are both valid single peaked orders. And so maybe I did have this picture here which probably reminds you of a normal curve. This was just to indicate the direction in which the preferences flow from the peak, just outwards, but that's all that it is depicting. So there isn't a more serious significance for this picture. It's just indicating that the preferences go downhill from the peak in either direction, but you still have plenty of room for doing the interleaving. Yeah. Does that answer your question? Yeah. Okay. Yeah, as I said, if you look at the data here, it isn't necessarily, yeah, I mean, these bars could have any structure, I think. Yeah, so it's pretty arbitrary even here. So these bars are just collecting the top vote statistics, the top candidate statistics from the voters. So that's all that we are staring at. Sorry, was there a question? Right, right. So for these voters, there isn't much of an option. If your favorite candidate is A, then the rest of your ordering is fully determined. There isn't any room for maneuvering. Similarly, if your favorite candidate is G, there is no room for maneuvering. That's a good point. Oops. Yeah. Okay, so coming back to the mechanism, as I said, um, we enlist the voters who vote for these candidates at the top, and we find the candidate who has amassed half the votes cumulatively, right? And that's the candidate that we output as the winner. So this is a social choice function. So I mean, of course, you could turn it into a ranking by eliminating this candidate from consideration, running the rule again, and then finding the next best candidate and so on. But for now, let's just focus on um, the social choice version of the mechanism, right? Okay, so the first claim here, which I think we should be able to prove, is that this candidate D beats every other candidate in pairwise elections. So does anyone want to take a stab at this? Sorry? All candidates, sorry, all voters you mean? Or, yeah, all voters have their peak, all voters in this column have their peak at D. All voters here have their peak at C on the second column, I mean on the third column, sorry. Yeah, so these are the guys. So whose favorite candidate is C, right? And I mean, so that's how the columns are defined. So maybe let's just see what happens um, if we ask D to battle it out with B, maybe, right? So really we are looking at a pairwise contest between B and D at this point. So who are the voters who prefer D over B, and who are the voters who prefer B over D? Maybe this is not the best choice, maybe so because B and D sound so similar. Yeah, C, yeah, hopefully I can make that sound distinct. So let's do C versus D. So notice that every voter whose peak is at D or to the right of D, they are all voters who are going to vote for, so all of these guys here are going to vote for D over C because their peak is to the right of D, right? So C is further away from the peak, and the voters who are going to vote the other way are here, right? So for them D is further away from the peak, so this is going to be C over D. And because of the choice of D being the median candidate, right? Because you're going to include these votes, right? So this is essentially you stop the first time that you cross half, right? So even if you look at it from the other side, this side is always going to be heavier, or it's going to actually be heavier than the other side. Yeah. So this is including the votes for D and the rest of the votes, right? So if this was less than half the votes, if this set was less than half, then, well, I mean, then this chap here is already more than half, and D would not have been the median. The median would have shifted to the left, right? So if this collection here, if this is less than half the votes, then this is more than half the votes. Then why did you go all the way up to D to identify the median point, right? You would have stopped short even earlier, right? So this is certainly more than half the votes here, which implies that D in fact does beat C in a pairwise election. And a very similar argument holds for any candidate to the left of D. And a symmetric argument holds for all the candidates who are to the right of D. If you are to the right of D, then again, people who are going to, so let's just quickly do this with maybe D versus F, for instance. So the candidates who are going to vote for F over D are, sorry, the voters who are going to vote for F in favor of D are the voters in the last two columns, right? Here you have that F is a favorite, and at G again D is further from G than F is. But everyone else is going to prefer, so if the peak is, so these are the guys who are going to vote for F over D, but all of these folks here, so certainly all of these guys here, and even if, okay, so I don't want to account for E, I think that would not be quite accurate, because when you peak here, D and F are on either side, and the interleaving could go either way. I don't really control that. So any candidate strictly between D and F, I'm not going to comment about them. But at least all the way up to D's column, all of these folks definitely have a peak either at D or to the left of D, which makes F further away from D from their point of view. So all of these guys are going to prefer D over F. Yeah, and then this is again by the same logic of picking the median point, this is strictly more than half the voters. Yeah. Does this explain why there are no Condorcet cycles? If you have a clear Condorcet winner, then you cannot have a majority cycle, right? All right, so that's at least somewhat sorted. So I think this, okay, the slides pretty much repeated the arguments that we made, so I skipped ahead. Here is the real deal that we were waiting for, which is to say that this is a strategy proof mechanism. So does anybody here have an incentive to deviate from their truthful choice? So first of all, notice that this mechanism has a flavor of plurality in the sense that it seems to be only accounting for who is at the top. It's making use only of that information, okay? But it does it in a slightly more sophisticated way because it also has this harmonious ordering in addition. So it's combining information from the top positions along with the harmonious ordering to do something interesting. So really, if you make any changes in your interleaving, for instance, if you don't change your peak, if you only change the way in which you interleave the orderings, will that affect the output of the mechanism? Okay, so these voters here certainly have no incentive to deviate because they are getting their favorite candidate, right? Their top candidate was D, and that's what the mechanism is giving us. Let's look at a voter here may be tempted to deviate. What I'm asking is, can she deviate by keeping C at the top and then changing the way in which she interleaves the orders on either side of C? Will that make a difference to the outcome of the mechanism? Yeah. Okay, that's a good question. When we talk about manipulation, can we deviate to a different ordering, which is not single peak? In this case, let's just constrain ourselves to manipulating within the space of single peak profiles. You could also consider what happens when you are allowed to do more. Um, and I think things may be slightly different in such a scenario. But here our point is that our preferences naturally follow a single peaked order. And one issue with deviating from such would be that you also run the risk of getting caught, right? I mean, a manipulator would also not want to raise suspicion. So one of the justifications for saying that the manipulated vote should also be single peaked is that you stay under the radar that way. If you go out of the norm, then that may just raise suspicion. So let's just work with the assumption that we are moving to a single peaked order. Yeah. So also even in the computational perspective, I mean, both versions are studied, but I think the more common assumption is that when you are working within a domain, your manipulative attempts also remain within the domain. It's a fairly standard assumption. So the first question is changing, I mean, if a voter in C's column continues to keep C at the peak and messes around with the rest of her preferences, I mean, in fact, for the statement that I'm making, it probably doesn't even matter as to whether the preferences, I mean, the ordering ends up even violating single peakness, because consider what the mechanism is doing. It's enlisting voters who have voted for C at the top position, and it's using this picture to make its decision, right? Will this picture change if your manipulations are such that they only happen beyond your top preference? So if nobody changes their top preference and they, even if they collude and they sit down and, try to do something interesting with the rest of their, with the rest of their rankings, will that affect the outcome of the mechanism? Okay, some of you seem to think that it will not affect the output of the mechanism, and why is that? So my question is, if no voter changes uh, the candidate that they place at the top position, then will the output of the mechanism change? So you go to another profile from this one, let's say, where the votes may be quite different, but everyone still retains the candidate that they have placed at their top position. Then will the output of the mechanism change? The mechanism in question here is the median candidate mechanism. This is the algorithm that we just proposed to output a winner was that we'll make this little histogram here and we will output the median candidate. Won't change, because the picture of the histogram stays the same, right? No matter what you do, if the top positions remain the same, then the way you're going to collect the voters also stays the same and nothing about the mechanism is affected. So if you want to have a serious shot at manipulation, then you have to change your peak, right? Otherwise, you will not be able to affect or influence the outcome of the mechanism. Okay, so suppose our friend here, the first voter in C's column, suppose she wants to attempt manipulating by changing her peak. What should she change her peak to? Where can she go? And does it make a difference if she changes the peak from C to B or C to A? Because that would just move this circle here or here, but the overall location of the median stays the same, right? It's the same story if she goes to D, right? What else can she do? She could potentially change her peak to something beyond D, like E, F, or G. So she could go and join one of these columns. How will that affect the location of the median? Will it move the median to the left or to the right? Right. Yeah, so if she moves to the other side of the fence, then the median either stays the same or in fact moves to the right, because you are making this side lighter, so it will take you longer to find the median, if at all, right? So the median candidate, well, either stays the same, in which case you achieve nothing, or if you did manage to change it, it actually moves rightwards. But since you peaked to the left of the median, if the median moves towards the right, the outcome is better for you or worse for you? Remember that your true preferences are at least single peaked, right? Even if your deviation is not. So if your true preference is single peaked, would you be happy if the median moved towards the right, considering that your peak was to the left of the median? No, right? Because that's only going to be further off from what you want. So if you move your peak to the right of the median, then you run the risk of worsening the outcome. And if you move your peak to the left of the median, then you don't change the outcome. So either way, you are pretty helpless. I mean, you cannot, you either don't change the outcome or you make it worse, which means that you actually do not have any incentive to deviate. And I think in this argument, you probably could even try deviating to a non-single peaked preference, but the same argument would work. In the sense that what the mechanism is doing is anyway taking the top positions, right? And what we said about the mechanism being a Condorcet winner may get affected if, I mean, that really depends on every vote being single peak. But in this manipulation, essentially, since any manipulation beyond the peak anyway does not matter, it's really a question of, you know, can you change your peak to something else? And the way the mechanism is set up, you just cannot. So even if the rest of your ranking is something fancy and potentially not single peaked, it will still not help. Okay. So is this clear that nobody has an incentive to manipulate with respect to the median candidate? Yeah. So I would say this is, yeah, so this is again trying to say that there's nothing interesting to be done here. Okay, so so one thing that I am actively omitting in the context of single peak preferences is the issue of identifying them. So this is actually an interesting algorithm, and it's actually pretty old as well. It involves setting up a matrix based on the rankings and checking if the matrix has this so-called consecutive ones property. So it's a binary matrix, all the entries are 0 or 1, and a matrix has the consecutive ones property if in every row all the ones appear contiguously. There is no break. So it's a run of zeros followed by a run of ones followed by a run of zeros, where the run of zeros, one of them may even be empty. So that is something that turns out to be, so we know how to check if matrices have this property. So the way this works is by reducing this to the consecutive ones problem. But I won't really be saying anything more about this. Maybe what I will do is give you the construction of the matrix. Again, probably a tutorial problem is the best place to do this. I will give you how the matrix is constructed from the permutations, and it's a nice exercise to figure out what consecutive ones has to do with single peakness. So again, that is something that I'm slightly deferring. In the interest of spending whatever time I have to tell you a little bit about multi-winner voting rules, this is something that I promise that I'll allude to, and we'll also see how domain restrictions can be interesting or useful in the context of coming up with efficient winner determination algorithms for voting rules which are kind of difficult to wrestle with in terms of even coming up with the winner. So let me just spend a couple of minutes drawing your attention to the fact that all the voting rules that we have discussed so far, I haven't really explicitly talked about algorithms for computing the winner with respect to these voting rules, mostly because the algorithms were straightforward from the definitions. So if you looked at Boda count or scoring rules or Copland, figuring out who has the highest Copland score or figuring out who has the best Boda score, all of these things can be, you can write little programs to compute these winners by pretty much following the definitions, and there isn't any challenges that you would run into. But from a certain point of view, winner determination is the most fundamental question you need to ask about a voting rule. When you come up with a voting rule, you want to know, well, is this voting rule efficiently computable? Can we actually work out who the winner is with respect to this voting rule quickly? And as I said, we haven't really encountered voting rules where the answer to this question would be tricky. So we have kind of bypassed it altogether. However, there are voting rules which are very interesting, but which are a little tricky to deal with, or you could say that they are unpopular in practice because it turns out that we don't know how to efficiently compute the winners with respect to some of these rules. So for instance, one voting rule off the cuff which has this sort of a situation is the Dodson voting rule, which basically is a voting rule that's in love with Condorcet winners. So the rule says if there is a Condorcet winner, then output it. But as we know, we may not always have a Condorcet winner. So the rule says what is the smallest number of changes that you need to make to the profile to make a particular candidate a Condorcet winner. Okay. So suppose you have a candidate C. The Dodson score of a candidate C is the smallest number of swaps that you need to make in the voters' votes to push C up to Condorcet winner status. So if you change the votes, of course, there is some possibility of eliminating majority cycles. And in particular, if you change the votes drastically enough, you will be able to get to the point of a Condorcet winner. But the question is, what is the smallest number of changes that you need to make a particular candidate C a Condorcet winner? That is the Dodson score of that candidate. So essentially you are asking, is a candidate really close to being Condorcet, meaning that maybe there are some silly voters whom you can adjust, whose votes you can adjust a little bit and then make C a Condorcet winner. So that's an idea that Dodson tries to capture. But I'd encourage you to think about how you would compute the Dodson score of a particular candidate. It's not obvious. Computing the Boda score of a candidate or computing the Copland score of a candidate, it was fairly easy from the definition. But from this definition, I'm not sure that it's obvious how to compute the Dodson score. Of course, you could try all possible ways of doing all possible swaps to the voter profile and seeing how it affects C's Condorcet status, and then go for the set of swaps which is the smallest in number. But this is a terribly inefficient approach, and maybe just come up with the complexity of this brute force approach. You will find that it is it's really bad. So it's certainly exponential, probably even double exponential. So yeah, so that's a fairly inefficient way of doing things. So can you come up with something that is better? So so that's a question that again I want to just leave you with. I'm not going to dig deeper into Dodson now, but I want to tell you about another voting rule which also feels very appealing, but has the issue that it's not easy, or it's not obvious how you can compute the winners. And I want to do an example in the committee setting, because that's a setting that we haven't touched upon yet. And one of the reasons for bringing this up is that we'll be able to also observe that if your profile happened to be single peaked, then actually there is a nice way of computing the winners efficiently. So that's another advantage of looking at restricted domains. I mean, not just resistance to manipulation, but some really nice voting rules which were out of reach just because they were hard to compute. Winner determination was tricky. They become more accessible because the structure of single peaked profiles lets you come up with interesting algorithms. So that's going to be the rest of the story here. Okay, so recall that the multi-winner setting is where again we have a collection of rankings, let's say, and we want to output a committee of size k, of fixed size. Okay, and in these slides, again the notation is that every row is a ranking, and the icons depict alternatives. Maybe again this is you folks trying to figure out how you want to spend the evening. So go out for dinner, go out for coffee, go out for a concert, or watch a football match. Should have been cricket, but anyway, okay, so we'll live with this. But okay, so these are a bunch of rankings, and what we want to do is in the multi-winner setting, we want to select, let's say in this case we want to select 2 options. We want to narrow it down to 2 options. So here is a particular here's a particular approach which says that basically I'm going to see, okay, so I'm going to ask myself how far do I need to go for every voter. How far do I need to go before I appease the voter? I mean, the voter says that, okay, now at least one of these options is something that I'm okay with. So for instance, if I pick the options of having coffee and going to a concert, the last 4 voters have these options at their top spot. So we are going to say that these voters are fully satisfied with this outcome, because there's at least one person in the committee that you have suggested, or there's one alternative in the committee that turns out to be their favorite alternative, so they are not going to complain. The people who are going to complain are the first 2 voters, for whom what has happened is that you need to go up to their second spot to be able to see at least somebody in the committee whom they whom they like. So up to, okay, so in the top position, the first 2 voters are like, we don't see anybody that we like in the committee. Okay, and so these voters are going to be, let's just label these as unhappy voters. But if I draw a line at the second column, then I see that at this point everybody has somebody that they like in the committee. Okay, so that's my, so you can think of this as putting up a dissatisfaction threshold. Okay, so how far do I need to go before I can be sure that for every voter there is an alternative before the line that I've drawn that actually exists in the committee. Okay, so that line is certainly not here, but I can just about manage here. Okay, so again, if you want to be a little more precise about this, you can define the dissatisfaction of a voter with respect to a committee as the rank of, so the voter looks at the committee and figures out who is her favorite candidate in the committee, right, among all the options. So I have a ranking, so I figure out who is my favorite candidate in the committee, right? So let's just say that the highlighted candidates in the bottom row are my choice of committee. So I go to a voter and I ask her, well, you know, who is your favorite candidate in this committee? So in this case, so let's say that the orange candidate is the voter's favorite candidate, right? The blue candidate is ranked last, let's say, and so her top two candidates didn't even make it to the committee, and the orange candidate is her best bet among the people who have been chosen in the committee. She likes the orange one the best. Okay, so the dissatisfaction of this voter, so again you could, what is typically defined as the border dissatisfaction. So if your favorite candidate got picked, your border dissatisfaction is 0, because it would be quite nitpicky of you to say that you have a dissatisfaction if your favorite person is in the committee. So the dissatisfaction is 0 if your top candidate is in the committee. But if your top candidate is missing and your second candidate, your second favorite candidate is present in the committee, then you have a dissatisfaction of 1, and so on and so forth. So it's 0, 1, 2, 3 and so on. So in this case, this particular voter that's highlighted has a dissatisfaction of 2, because it's the third, I mean her third ranked candidate is her best bet in the committee. Okay. So there are two versions of, or there are two ways in which you can evaluate a proposed committee. Either you could look at, you could write down all the dissatisfaction scores, and you could, I mean, are there, what do you want to do with these dissatisfaction scores? So you could add them up, and you could say that you want to minimize the sum of all the dissatisfaction scores. Or you could also take the worst dissatisfaction score and you say that you want to minimize the maximum dissatisfaction. Okay. Yeah. So the size of the committee is fixed. That is correct. How can we make sure that the sum is, so we just